This is a little video lesson on 7.1, the Pythagorean Theorem. We're going to use the relationships within triangles to find side lengths of right triangles. So a little history lesson to start. One of the most famous theorems in mathematics is the Pythagorean Theorem. The Pythagorean Theorem is named after an ancient Greek mathematician named Pythagoras around 500 BC. The theorem can be used to find information about the lengths of the sides of a right triangle. Okay. The theorem goes as said right here: if triangle ABC, which if I pause real quick, look at this triangle here. This is side little a. Side little a is opposite of angle big A. Side little b is opposite of angle big B. And side C, which is opposite of the right angle here, and that's angle C. So, given that triangle ABC is a right triangle, then C squared is equal to A squared plus B squared, where A, B, and C are all the sides opposite of those specific angles. Now, I don't like using A, B, and C, mainly because C, A, and B are arbitrary. They're just variables that are using as placeholders for side lengths of a right triangle. So rather than using A, B, and C, I always help my students remember the Pythagorean theorem is like hypotenuse squared is equal to leg squared plus leg squared. Hypotenuse squared is equal to leg squared plus leg squared. When I look at my picture here of my right triangle, the two sides adjacent to the right angle are the legs, and the side opposite of the right angle, or angle C, here in this case, is the hypotenuse. So you can use those features to help remember which side is being squared and which ones are added, and that'll be a helpful formula for us to know. So here's a few practice problems with the Pythagorean theorem. Here we have a right triangle. I know it's a right triangle because this angle right here is a right angle, so the side opposite of that right angle, that's the hypotenuse. The two sides adjacent are the legs, denoted with L's. So if I'm using the Pythagorean theorem to find the missing side length, the hypotenuse, I'm going to do the hypotenuse squared is equal to the sum of the two legs squared. 8 squared plus 6 squared. At the beginning of this lesson, I really made sure that you guys wanted to remember that when you're using Pythagorean theorem and you're just going to be squaring a lot of side lengths, you have to understand your perfect squares very quickly. So when I look at 8 squared, a lot of you should be able to pull out what that number is from your math facts. So 8 squared is 64, where 6 squared is 36. Now that I've squared both of those using PEMDAS and doing exponents first, now I can add the like terms. 64 and 36 add up to 100. And to undo a square, I need to square root an equation. So by square rooting a square, all I'm left with is x. What I do to one side, I have to do to the other. So what's the square root of 100? Using my perfect squares, the square root of 100 is going to be 10. So the hypotenuse in this problem is x equals 10. We're going to look at example 2 here. Go ahead and pause the video and try it first on your own. And then once you feel like you've gotten it, you can play the video and watch it through its steps. So here's my right angle. The side opposite would be my hypotenuse, and the two adjacent sides would be my legs. So using Pythagorean theorem, 5 squared, the hypotenuse squared would equal the leg squared plus the leg squared. 5 squared is a perfect square, so that's going to be 25, plus 3 squared, which is 9. In this case, I have a 9 and 25 on opposite sides of the equation, so I need to subtract 9 from both sides to combine like terms. Left with a 16 is equal to x squared, and then when I go ahead and square root both sides, I get a value of x to be equal to 4. We're going to look at 2 word problem examples. Go ahead and read those to yourself. And we're going to try to draw a picture first. So here we have a 16-foot ladder that's resting up against the side of a house. So we have a house here, and we have a ladder. That ladder is 16 feet long. That's my house here on this side. The base of the ladder, which is down here, it's the base of the ladder, is 4 feet away from the house. So here, this distance is my 4 feet. As long as it's a well-built house, we know that the house to the ground must be perpendicular, so that must be a right angle. How high above the ground is the top of the ladder? So we're now asked to find how high from the top of the ladder to the ground, how tall is the ladder standing right now. So using our Pythagorean Theorem, we're going to find the hypotenuse is opposite of the right angle, so that's 16 squared is equal to leg squared plus leg squared. So here I'm going to take x squared plus 4 squared. You might not know 16 squared off the top of your head, that's right, you have a calculator. If you plug that in, or if you have that one memorized, 16 squared is 256 equal to x squared plus 4 squared is 16. Subtract 16 from both sides, and you have x squared is equal to 240. And when I square root that, since this is a practical problem, and most likely when you're looking at this type of problem, you're not going to go ahead and give your answer in the simplest radical form, and they say round to the nearest tenth, we can go ahead and put this in our calculator. The square root of 240 is about 15.5 feet. So the height of the ladder from the base of the ground is about 15.5 feet. Find the area of this isosceles triangle with the side lengths of 10 meters, 13 meters, and 13 meters. So I went ahead and gave you a picture of an isosceles triangle there. The two sides that are congruent in an isosceles triangle are the legs, so both of these are going to be 13 and 13. The base here is a length of 10 meters. When I'm looking at this example, and we're asked to find the area of a triangle, we have to remember what the area formula is. So when I look back at my notes, or I think back to middle school math, area of a triangle is equal to 1/2 the base of the triangle times the height of the triangle. In my example so far, I know what the base is. The base is going to be equal to 10 meters. But the height's a little more difficult than that. The height is not the slanted height that was given in one of the sides of my isosceles triangle. The height has to be a perpendicular distance from the base. To be an actual height, think about it. When you go to the doctors or wherever they measure you for your height, you have to stand straight up and down, as very tall as you can. So we're going to look at the height as this distance right here. So once I draw that perpendicular distance from the base, I then form a smaller right triangle, where the hypotenuse is 13 because it's opposite of the right angle. We don't know the height. And what's this value that's going to be at the bottom? Since this is an isosceles triangle, this perpendicular line is also going to bisect the base, meaning that this smaller piece is going to be 5. That only happens because it's isosceles. So now that I've given this little red triangle, now I can use the Pythagorean Theorem to set the hypotenuse squared equal to the leg squared plus the leg squared. Because it's a right triangle, I can use Pythagorean Theorem. 13 squared is 169. H squared plus 5 squared is 25. When I subtract 25 from both sides, I end up with a value of 144. And since I can square root 144, I get h to be equal to 12 meters. So the height here in this case, we know is 12 meters. And now we can plug into our area formula to find the missing piece. Area is going to be equal to 1/2 the base, 10, times the height, 12. So the area of my triangle is 60 meters squared when I plug those values in. So another way to kind of use the Pythagorean Theorem is recognizing that there are a certain sets of 3 positive integers, such as a, b, and c, that satisfy the equation a squared plus b squared equals c squared. There are common triplets, we can call them, that always form a right triangle. So, the most common ones that we usually see in this class are as follows. We have the 3, 4, 5 triangle. We have the 5, 12, 13 triangle. We have the 8, 15, 17 triangle. And last but not least, we have the 7, 24, 25 triangle. These aren't the only Pythagorean triples that exist. There are others out there that you can find. And we'll find 2 more here later on. But let's go ahead and understand that because these triples are true, if I would multiply them by a scalar value, if I would multiply these by a scalar value, scalar value is just the same number repeated. If I multiply them all by maybe, for example, like 2, if I multiply them all by 2, what do I end up with? Well, 2 times 3 is 6, 4 times 2 is 8, 5 times 2 is 10. If I plug those in by Pythagorean Theorem, they also give me something that's true. If I multiply them by 3, I end up with 3 times 3, which is 9, 3 times 4, which is 12, and 3 times 5, which is 15. So basically what you're saying is if I multiply all these by the exact same number, I can get something that will fit the Pythagorean Theorem. That's true. Same thing would be true then for 5, 12, 13. 5 times 2 is 10. 2 times 12 is 24. Sorry, 12 times 2 is 24. 13 times 2 is 26. And the same thing would be true with the multiplying by 3. 15, 36, 39 are sides of a right triangle. So again, these ratios are very helpful to memorize if you're trying to remember all of your triples. We also have 8, 15, 17, which if I multiply them all by 2, I end up with 16, 30, and 34. For multiplying by 3, I end up with 24, 45, and 51. So that pairing is also multiplied by any scalar will give me a right triangle. Last but not least, we have 7, 24, and 25. Multiply them all by 2. You get 14, 48, and 50. Multiply them by 3, you get 75, 72, and 21. So we're going to follow that exact same pattern for all of my triples. So let's go ahead and use our triples and our Pythagorean Theorem to see which might be the easiest for you to remember. Again, no one way to do it. There's just 2 different ways, and you guys can kind of choose your method. So we have method 1 and we have method 2. Method 1 will use the Pythagorean Theorem. The Pythagorean Theorem tells me that I can take the side opposite of the right angle, which should be x squared, and that would be equal to the sum of the legs squared. Already you can see you have to kind of do some bigger multiplication there. So if I would go ahead and do that, I would get 24 squared, which is 576, plus 100, which adds up to 676. And when I square root that, I get x is equal to 26. The other method is with the Pythagorean triples. So with Pythagorean triples, I can kind of look at those side lengths. The smallest leg is 10, the next leg is 24, and the hypotenuse is always the largest side. So when I look at those 2 numbers, 10 and 24, I need to either remember my list here and kind of find where am I going to look for. So 10, 24 would have to go with x equals 26, but how would you know that without memorizing all of your triples? Well, 10 and 24, they both share a common factor of 2. So if I would go ahead and divide this by 2 and divide this by 2, that would mean I would get a value of 5 and 12. So hopefully if you see 5 and 12, you're going to think 13. So divided by 2 to get 13, multiply 2 gives me 26. Common mistake that students like to make when they're given two sides of a right triangle, they assume that because the legs are 3 and 5, that if this is 3 and this is 5, it's a right triangle, then the fourth side has to be 4, correct? Well, that's not always the case, because can the hypotenuse, which is the largest side, can that be equal to something that's less than one of the legs? No, that doesn't work. It fails. It does not pass the triangle inequality theorem. Which states that the largest angle, which in this case is the right angle, has to be opposite of the largest side. And since that angle is larger than any acute angle that could form a right triangle, that would mean that 4 is greater than 5, but that's not true. So because it fails that, we know that it can't be a possible side length. So here's some other example of kind of applying what we know about Pythagorean triples. What happens if you know two sides and you need to find the third? To do that, we're going to have to kind of determine whether it's a leg or a hypotenuse by use of Pythagorean theorem. And if it comes out to an integer, then I know I have the right side. If it's not an integer, then I know I did it incorrectly. So let's go ahead and let's just assume that 28 and 45 for this example are both legs. And if we get out to something that's a decimal in our calculator, then we know we need to try it as if the 45 is the hypotenuse. So let's go ahead and take 28 squared plus 45 squared. The sum of those two values squared need to be equal to the missing side squared, which is our hypotenuse. So we'll go ahead and put those into our calculators, which are relatively large numbers. So when I go ahead and square 28, I end up with 2,809 in my calculator, plus, nope, I'm sorry, let me backtrack there. When I put that in my calculator, I'm going to do 28 squared plus 45 squared. When I add those two squares, I end up with a sum of 2,809. The last step I'm going to have to do in my calculator is the square root. And remember, if our square root ends up, this value ends up being less, or a fraction, or not a fraction, a decimal, then I know I did it incorrectly. If you have something stored in the previous answer spot, you can always hit second negative sign, which will put in whatever that answer is under the square root. My value comes out to 53. So if the missing value is a whole number, or an integer, positive integer, then I know that I found the correct side, which makes this side the hypotenuse. So let's try the same thing for B. Let's see if it works. We're going to go ahead and plug these in as legs into my Pythagorean theorem. We're going to jump to our calculator, and we're going to go ahead and square those. So here we're going to take 56 squared plus 65 squared. And when I square those and add them together, I end up with 7,361. The last thing I need to do is square root. Again, if I get an integer, then I know I did it right and I found the hypotenuse. If I don't get an integer, then I know I didn't do it wrong, but I know that my answer cannot be a hypotenuse. And we end up with a decimal. We get 85.796, which means that if these were two legs of a right triangle, the third side would not form the Pythagorean triple. So at this point, we're going to have to kind of cross out what we did, and we're going to have to go a different route. So let's assume that the missing piece, 56 and 65, let's assume that the missing piece is not the hypotenuse but a leg. That would mean that the larger of the two sides given has to be the hypotenuse of my right triangle. So now let's assume 65 is my hypotenuse, and we'll square that and set it equal to 56 squared plus x squared, one of the missing legs. So in my calculator, I'm going to go ahead and do 65 squared, which is 4,225. And we're going to do 56 squared, which is 3,136. And because they're on opposite sides, we're going to have to take the difference of those two numbers. So 4,225 minus 3,136 will give us a value of 1,089. Square rooting. When I square root that value, I end up with 33, meaning that it is a missing leg, and I know that this side of 33 is a leg of a right triangle. So that wraps up our notes here on 7.1. Make sure you try the, if you still don't understand it, go back over the video, start the homework, give it a shot, and we'll talk about it next class.